Okay, hello class. Now look at questions 3 to 15, possibly at a go. I had to cut short the other lecture because I didn't want to over explain so that you will not be bored. Now to question 3. Calculate the first three energy levels in joules for an electron confined to a one-dimensional box of length 2 nanometers. What will be the wavelength of light absorbed for a transition from n equals 1 to n equal 2? So how are you going to approach this? So yeah, you need to bear in mind a particular equation, which is En is equals to n square h square over 8m l square. Remember, you said for the first three energy levels, right? So that means your n equals 1, 2, and 3. So bear that in mind. And your L is given as 2 nanometers. So M, which is the mass, will be 9.109 times 10 raised power minus 31 kilograms, and L is equals to 2 times 10 raised power minus 9 meters. Okay, so this is our equation here. So what has been done here? So you still have your n. So for this first one, n equals 1. That's why there's nothing here. You can see look at my cursor rather. So there's nothing here. So remember n square. So we are looking for the level n equals 1, right? We are starting with 1. So and 1 square is equals to 1. 1 times anything is that thing, right? So that's why it is h square over 8m l square. So because it's 1. So and then we have 6.626 times 10 raised power minus 34 all squared over 8 times 9.109 times 10 raised power minus 31. We know that is m. And our L, of course, 2 times 10 raised power minus 9. So where did we get our 10 raised power minus 9 from? Is because the length is in nanometers. Nano means 10 raised power minus 9. Okay, wherever you see nano means 10 raised power, that's nanometers. So that's why it is 2 times 10 raised power minus 9. Remember, it's squared, right? So squared. So that gives us overall 1.506 times 10 raised power minus 20 joules. Now to the second one, all you now need to do to get the second one is to put 4 here. Remember, it's 2 square. So that's 2 square is 4. So now it's going to 4h square over 8m l square. So that should give you 6 points. So in a test condition, you have to calculate for each of the 3 energy levels. Okay, so let me see your calculation, how you got it. Then for the third one, remember n is 3 now, so it's going to be 9h square over 8m l square. So that should give you 1 point. So that is actually 13.55 times 10 raised power minus 20. Okay, so which has been approximated to this. Okay, now remember, we are now talking about that's the second part of the question. Say, what will be the wavelength of light absorbed for a transition from n1 to n2? So there you see a transition n1 to n2. So remember, we have for n1 E here, for n2 E2, right? So all you now need to do is to subtract, and that's 6.02 minus 1.51. Okay. And there you get 4.51 minus 10 raised power minus 20 joules. So that's what you get. Now the corresponding wavelength, remember delta E is equals to hf, right? That's frequency, and frequency is c over lambda. And when you make lambda the subject of formula, you get this equation, right? You can see it there. So lambda is equals to hc over delta E. Yes, so remember h is our Planck's constant, which is 6.626 times 10 to the power minus 34, times c is the speed of light, which is 3 times 10 to the power 8, over, then we have our delta E already, which is 4.51 times 10 to the power minus 20. Your answer should be 4.41 times 10 to the power minus 6 meters. So, okay, you can make it up into a nanometer, so that will give you this value. Okay, so let's move on to question 4. Question 4, where we look at Heisenberg uncertainty principle. Okay, very interesting principle. Now, if an electron is confined to a space of 0.1 nanometers, okay, which is approximately the size of an atom, use the Heisenberg uncertainty principle to estimate the minimum uncertainty in its momentum and then its velocity. So there you have it. Then you are given mass of electron to be 9.109 times 10 to the power minus 31 kilograms. So now, what is the Heisenberg uncertainty principle? So there you have it. Delta x times delta p is greater or equal to the reduced form of Planck's constant over 2. So I'll call it h bar. Okay, that's a reduced form of Planck's constant. That's h with that bar. Can you see it? Okay. Now, remember the question said minimum uncertainty. So remember the equation said from is greater or equal to. So that means the minimum will be equal. You understand? So that means you have to use this equation. You have to change that to delta x times delta p is equal to h bar over 2. Okay, h bar over 2. And so we remember we are looking for the momentum. Okay, first. So that will be delta p. Make delta p the subject of the formula, and then get delta p is equals to h bar over 2 times delta x. Okay, and so we can move on to say, okay, remember you have delta h, that's your reduced h bar. Sorry, your h bar will be, that's your reduced form. So you might be asking a question, why is this h different from the other h we used earlier? So this is the reduced form of Planck's constant h bar. Okay, so the other h does not have a bar. Okay, this one has a bar. So this is 1.055 times 10 to the power minus 34, then over 2. So 2. Remember, we have a space here, that's our x, 0.1 nanometers. So 0.1 nanometers is 0.1 times 10 to the power minus 9. Okay, you can convert it to 1 times 10 to the power minus 10. Whatever one you use, you get the right answer. So your final answer should be 5.275 times 10 to the power minus 25 kilogram meter per second. So that's your answer there. Now remember, you have a second consideration. We've gotten the momentum. Now we are looking at the velocity. So velocity, remember from your basic physics, okay, momentum is equals to what? Mass times velocity. So when you make velocity subject of formula, it is going to be delta v is equals to delta p, which is momentum over mass of electron. And so we have our answer there already, 5.275 times 10 to the power minus 25 over, remember you are given the mass of electron as 9.109 times 10 raised to the power minus 31. So your delta V should be 5.79 times 10 raised to the power 5 meters per second. So that's your answer. Now we move to question 5. So for question 5, we are looking at angular momentum. Okay. So here we say compare and contrast classical and quantum angular momentum. Why does the quantization of angular momentum explain atomic stability, whereas classical angular momentum does not? So for compare and contrasting, you can put it in a tabular form to make it easier for you. And then we have different aspects, right? So we have it in this tabular form. Let me make that. So these are the titles, and then we look at the values. So what's the value for classical? It's continuous. The value for quantum, quantized. Magnitude for classical is L is equals to L omega. For quantum is L is equals to H square root of L times L plus 1. Okay. Then for direction, any direction, okay, any direction, that's for classical. For quantum, it is, you have limited orientations, okay. For components, for classical, you have all three components, okay. All three components can be known precisely, that's for classical. But for quantum, all three cannot be known simultaneously because of uncertainty principle. Now for visualization, we can say to visualize it, that is, how do you visualize it in your mind? Okay. So you have to look at probably the planetary model to visualize the classical angular momentum. But for quantum, you visualize it by looking at vector precessing around the quantization axis. Now for mathematical basis, so this is derived from R times P, while for quantum mathematical basis we look at the eigenvalues of angular momentum operators. So this is how you compare and contrast the classical and angular momentum. Now, why does it explain atomic stability? So this is simple. So all you need to just say here is, so when a charge, okay, a charge, accelerating charge is orbiting or going around is going around like a circle, okay, circular motion, okay, and for instance like a nucleus, it will radiate energy continuously, that's classical, but this will cause the electron to lose energy and spiral into the nucleus, okay, but of course we know that is not the case. So because of quantization of angular momentum, okay, this is important. So that is why the atom is stable. Okay, now we move on to another important question here. So question 6. So for an electron in a state with azimuthal quantum number, we talked about principal quantum number, azimuthal quantum number, magnetic quantum number, and even the spin quantum number. So remember that. So for an electron in a state with azimuthal quantum number L equals to, what are the possible values of the magnetic quantum number ML? So, and what are the possible Z components of angular momentum? Okay, so now for an electron with azimuthal quantum number L equals to, okay, remember when L equals to, then our M can be -2. You can see it here, can be -2, -1, 0, 1, or 2. So if that is the case, then what are the possible values of the magnetic quantum number? So we have them there. Okay, now we are looking at the Z component. So the Z component is just that your Lz is equals to MLH, and so your answer will be Lz is equals to, remember we said that these are the possible values, right? So you just add h bar to it. So -2 h bar, instead of saying -1 h bar, because just a minus h bar is the same thing, right? Then 0 h bar is 0, that's why you have 0 here. 1 h bar is, of course, h bar, and then you have 2 h bar. So that's the answer here. Okay, now we move on to the next question. What is space quantization? How does it differ from classical expectations? So space quantization is the quantum mechanical principle that the orientation of an angular momentum vector in space is restricted to discrete allowed directions relative to a chosen axis, usually an external field direction taken as the z-axis. Okay, so that's space. I've explained what space quantization means, okay, in the other class. So you're talking about angular momentum, okay, the electron having a fixed that's energy, okay. So, and for this question, this should be a sufficient answer, okay. So this is a sufficient answer. Now, how it differs from the classical, so from the classical mechanics. So what you have there is, there you have discrete value. So this is all. So here you have discrete values. So that's how it differs. Okay. So that's your answer. Now starting from the, I'm sure you have done this. So with the starting from the time dependent Schrodinger equation for the hydrogen atom, show how separation of variables leads to a radial equation and an angular equation. So all I need is to adjust the variables, okay, the radial equation and the angular equation. Simple. So you first of all give the, you can see it here, you give the Schrodinger equation, okay, so that is it, and then you give the variables. What are the variables? So you can see the variables there, and then you give the radial equation and then the angular equation. So that's all. Okay, now we move to, so please take this seriously. You need to practice this so that you get used to it, so you don't make mistakes. Okay, so this might look, it's not something you can just rush in a day, so it's something you need to start practicing. So please practice. Now identify the quantum numbers that emerge from solving the equations above. So yes, so what are the quantum numbers you get from solving the Schrodinger equations? That's the radial and the angular equations. Okay, what are the quantum numbers that you get out of it? So simple. And then remember, you talk about what is the physical significance of each quantum number. So remember, you are doing two things. You give the quantum number and the physical significance. So let's start with the first one. So for this question, only 3 quantum numbers emerge from the Schrodinger equation, which are the principal, azimuthal, and magnetic quantum numbers. So now the physical significance. So principal determines the energy and the overall size of the orbital. Azimuthal determines the magnitude of orbital angular momentum, while magnetic determines the z components of angular momentum and the orbital orientation. So these are the physical aspects of each quantum number. Okay, now we move to our next question, that is 10. So how many distinct orbitals are possible for an electron with principal quantum number n equals to 4? So you have a principal quantum number n equals 4. So show your calculation considering all possible L and ML values. So when L equals to 4, then L can be 0, 1, 2, or 3. Okay, so L can be 0, 1, 2, or 3. That's the first step. Next step, remember we are looking at how many states are possible when n equals to 4. So we know that L is 0, 1, 2, or 3. And for each of these L, okay, you have ML ranging from minus L to plus L. So you can just simply put down this table to make it easier for you. Okay, so remember when L equals to 0, then M is equals to 0. So you have only one state here. Then when L is 1, M is minus 1, 0, plus 1. So you have 3 states. Then when L is 2, M is minus 2, minus 1, 0, plus 1, plus 2, 5 states. Then now when L is 3, then M can be minus 3, minus 2, minus 1, 0, plus 1 to 3. So 7 states. So what you do next is to add all the states so that we can know the number of distinct states possible. Okay, so it's going to be 1 plus 3 plus 5 plus 7, which will be what? 16. So the 16, we have 16 distinct orbital states, right? So that's the answer to that. Okay. Now we move to 11. Hydrogen atom in the 3D state. Hydrogen atom in the 3D state. So in this state, we look at, remember 3D. So when you talk about 3D, N is equals to 3. And for D, L is equals to. Now for the magnetic quantum number, when L is equals to 2, then your M will be minus 2, minus 1, 0, plus 1, and plus 2, right? Then the possible sets of, remember, list all possible sets of quantum numbers N, L, and M. So what are the possible sets? So what is changing is your M, right? So you have 3 here, 2. So these ones are constant all through the sets. What is changing is your M. So you have 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, plus 1, and 3, 2, plus 2. So how many sets do you have? 1, 2, 3, 4, 5. So they should be 5. Now to the second sub question here. Calculate the orbital angular momentum magnitude. So this is the equation for the orbital angular momentum magnitude. So L is equals to square root of L into L plus 1 h bar. But remember from our question, L is equals to 2, right? So we have L is equals to 2 times 2 plus 1 h bar. And so your answer will be square root of 6h bar. So you can stop there. So that is what is needed. Now to the third sub question there, you have calculate the energy difference between this state, what's this state, 3D, right, and the 2p state. So what is the energy difference? Now the energy difference will be, remember we are using remember we are looking at EV, electron volts. So this is what you're going to use. En is equals to minus 13.6 over n square EV, right? So the energy of the 3D state will be E3 is equals to minus 13.6 over n square, that's 3 square, that's 9, and that will be minus 1.51 EV. Now for the 2p state, there is now going to be over 2 square, which is 4, and that is going to be minus 3.4 EV, minus 3.4 EV. Bearing that in mind, the energy difference will now be delta E is equal to E3 minus E2, which is equal to minus 1.51 minus 3.4, and that gives us 1.89 electron volts. Now to question 12. Yeah. So a hydrogen like ion, okay, you know what, remember I talked about hydrogen ion the other time. So the hydrogen like ion emits light at 30.4 nanometers when an electron transitions from n is equal to 2 to n is equal to 1. Identify the ion and show your calculations. What is the ionization energy of this ion? So 1, identify, then 2, ionization energy. So the first thing is you use the Rydberg equation, which I'm sure you are familiar with now. So and then you look at, okay, you have a transition from N2 to N1, right? So what you get there is, so remember 1 over, this should be 1 over, so N1 square minus 1 over N2 square. And so you have 1 over lambda is equals to RZ square, then in bracket 1 minus 1 over 4, and that gives us 3 over 4 RZ square. So this is your answer. Okay. Now we are looking at step 2. You substitute the given wavelength. Okay, the given wavelength. So the given wavelength here. So remember, you are given the light wavelength of light. So it emits light at 30.4 nanometers. So that is equal to 30.4 times 10 raised to the power minus 9. Remember, I told you nanometers means 10 raised to the power minus 9 meters. So if that is the case, then we can rightly say 1 over lambda is equal to 3.29 times 10 raised to the power 7 per meter. Okay, so we are inverting it. So this is an inversion. Okay, so when you invert it, that's 1 over, so what you have just done is just 1 over that value. So you get this. So now you can now equate it to the one above. Okay, so now you can say 3.29 times 10 raised to the power 7 is equals to 3 over 4, which is what you got earlier, times Then our Rydberg's constant, okay, so that is 1.097373, so which is okay times 10 raised to the power 7, okay, so times 10 raised to the power 7. Let me correct that. So 1.097373 times 10 raised to the power 7. I'm using the right thing. Okay, so I'm changing that. Yes, so to avoid any confusion. Okay, so here too, this is per meter, so this will raise to. Okay, so that is done. So we have our Rydberg's constant there, okay, which we input, that's our R. So we have it 1 point z square. So now we have our z. Now z square, you make z square the subject of formula, and then you get approximately 4. Okay, yeah, you approximate to 4. So remember, z square is equal to 4. That means z is square root of 4, which is 2. So that's why z is equal to 2. Now, that is it for the z there. So now remember, we're now looking at identifying the ion, which is now our first solution. That's your first answer. So you have to identify the ion. Okay, that's what you're supposed to do. So when z is equals to 1, okay, you know that's hydrogen. Yeah, that's your atomic number. When z is equals to 2, then you know that it is helium, right? Helium is next to it. So that means our hydrogen-like ion is actually helium, but it's helium with a plus, right? It's a plus because that's lost one electron. So that is it. So that's why it is hydrogen-like. I hope you understand. Okay, now to our next answer, we want to look at the ionization energy of this ion. So what's the ionization energy? That's simple. Remember, we used this in an inverted way before. So it's equals to E, energy of the ion, times Z square times 13.6 electron volts. So Z square times 13.6 electron volts. So now that we have our Z square already, which is 4, right, times 13.6, and that gives us 54.4 electron volts. So that's your answer right there. Now to question 13. So we're about to finish this. We are going to question 15. So to question 13, Stern and Gerlach experiment. Stern and Gerlach, if you wish, experiment. So this experimental setup, okay, used by Stern and Gerlach, okay, so it involved, so let's move here. So this is what is needed. Okay, so it involved a beam of silver atoms emitted from an oven, okay, collimated and passed through an inhomogeneous magnetic field. This is important, okay, inhomogeneous magnetic field with a gradient along the z-axis. So the atoms were then detected on the screen, and from what was observed, the beam split into 2 distinct spots corresponding to 2 discrete deflections, upward and downward. Okay, now the 2 beam results led to the postulate that electrons possess an intrinsic angular momentum called spin, with quantum number s equals to half, and another one, of course, we now know minus half. So the ms plus half is a spin up, while the ms minus half is a spin down. So that's how to answer that question. Now, this is something, and the reason why I've tried to compress this is to make it easier for you to comprehend, okay, and to assimilate. So here you have to compare three forms, okay, of three models. So here you have three model systems: particle in a box, which you have done. Then you have particle on a ring, which is the second one. And then the third one is hydrogen atom systems. Okay, I'm using 4 parameters. So I can ask you 4 or 5 parameters. Okay, so how many parameters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9. So I can give you 4 or 5 parameters that you should check there. You should compare. So kindly read through, okay, so that you'll be able to, and it's something you have to really practice, because you can mix things up if you are not careful. Okay, so this should be infinity. Yes. Okay, now you can look at potential energy. So you have it there: potential energy, boundary conditions, okay, coordinate system, quantum numbers, quantized quantities, energy expressions, so the different energy expressions, okay, then degeneracy, okay, wave function form, physical significance. So these are the different aspects you can use to distinguish between the particle in a box, particle on the ring, and the hydrogen atom model, okay, or system. So kindly work on this. So this might need some time. You need to practice. Okay, now to our next question. I think we're about to finish. Yes, the last one. So electron speed. Explain the concept of electron speed. What are the physical consequences? So what are the physical consequences of electron spin? So electron spin is an intrinsic form of angular momentum. Remember, we have said that earlier when we were describing the Stern and Gerlach experiment. Okay, so it is an intrinsic form of angular momentum that electrons and other fundamental particles possess, even when they are at rest. So now we look at that is what I really need. That is what I need from you. So you can take the other line. Yes. Next, physical consequences. I'm sure you are used to some of these. The Pauli's exclusion principle, very important. Okay, the magnetic moment and the doublet structure. So these are the three physical derivatives, okay, of the electron spin. So I think with this we come to the end of my lecture on quantum chemistry. So we come to the end of my lecture. So if you have any question, you can let me know. Okay, yes. So I'll see you in class.